So I'm going to talk about the analogous problem at other primes. And it's two different stories, really. One story is for primes bigger than 3, for which the problem was solved 40 years ago. And then there's the prime 3, for which it's still open. Now, there's 2 sources for this material. Just about everything I'm going to say is written down in one of 2 places. There's a preprint dated 2011 that you can find on my publications list. And then there's chapter 6 of the Green Book. Has some of this material, the old stuff. Okay, so what are we talking about? At p equals 2, we have a hypothetical element. Well, it's not hypothetical. We have the element known as theta j, which is hj squared, that lives in x over the Steenrod algebra in this bigrading. And hj itself lives in x1, 2 to the j, and it's related to the Steenrod operation, square 2 to the j. Now, let me make a profound observation here. 2 to the j is that. P is 2. So you can check that this equation is correct. The reason I'm doing this is that this is the dimension of square 2 to the j. At odd primes, there's a Steenrod operation that is denoted like this, and its dimension has a similar form. And it leads to an element, hj minus 1, that lives in x1, the same number here. And it has a p-fold Massey product that I'll denote. It's the p-fold Massey product. So this is the element. This is an element in that phi degree, and I'm going to rename this element theta j. So this is the odd primary theta j, so it's defined to be this element. Now, for p equals 3, the dimension of theta 1 works out to be 10. Theta 2 is 34. Theta 3 is 106. So in each case, I'm taking the difference of these 2 indices. And for p equals 5, the numbers are 38, 198, and 998. Now, you could say the odd primary Kervaire invariant or arc invariant problem is the fate of these elements in the atom spectral sequence. Now, the two primary elements have an interesting connection to manifold theory, surgery, and the work of Kervaire-Milner classifying exotic spheres. There is no such connection that I'm aware of these odd primary theta j's. The analogy between them rests on how they're defined in the Adams E2 term. In this case, in both cases, we have an element that's denoted by either Hj or Hj minus 1, and the reason for that discrepancy has to do with the notation that's used for the Steenrod algebra at various primes. That leads to that discrepancy. Anyway, this guy is the square of something in X1, and the square is the same thing as the twofold Massey product or the p-fold Massey product for the prime 2, and in general it's a p-fold Massey product, and you end up here. So the question is, what happens to these elements?
Doug,
Yeah.
for the p equals 3 case, is theta 1 known to be an infinite cycle?
Yes, it's beta 1. Yeah, it's in the 10 stem. Yes, it is known to.
And what about the other primes?
It's same. So so here's what's known. Okay, so I proved the following in 1978. If the prime is at least 5, beta 1, also known as beta 1, is a permanent cycle. But all the other cases all the higher theta j's fail to exist, and moreover, there's a differential in the spectral sequence that looks like this. The differential on theta j is alpha 1 times theta j minus 1 to the p, where alpha 1 is the same thing as H0, which I mentioned over here. H0 is lives here. And I'm calling it alpha 1 because that's the name of it. It's also a permanent cycle, and it corresponds to an element in the image of J. It's the first. It's the it lives in this dimension. It's the first positive dimensional element in the p-local homotopy of the sphere spectrum. Now, Toda, there's an important precursor to this is a theorem of Toda that I'll mention now. Now, Toda's theorem applies to all odd primes. And it's this differential in the first case. This theorem is used to prove this theorem. The proof of my theorem of 1978 amounts to using some fancy chromatic machinery, which was only very recently available at that time, to leverage Toda's differential in this case, in the case j equals 1, to, or I guess it's j, let's see, it said it's wrong. Okay, to leverage Toda's differential into all the differentials.
Does this element appear in unstable for S3?
What?
Alpha 1.
Yeah, it does. It does. Right. If you take, here's a quick way to construct alpha 1. start with this guy. Take the complex projective space of dimension P, suspend it once, and then it's possible to show that when you do that, it splits. It has the following structure. Well, first let me say it this way. If I do this for CPP minus 1, then if I suspend it once, then this happens P locally. You suspend CPP minus 1, suspend it once, and it has this splitting. It decomposes. It's a wedge of spheres in the appropriate dimension. Now, if you attach one more cell to it, so we go up this, we look at this suspension of p-dimensional complex projective space. Then we're looking for one more cell in dimension 2p plus 1, and that cell is attached to the bottom cell by this map alpha 1. So okay, so that's one way to construct alpha 1, it's that attaching pattern. Now, I wasn't planning to go into this in any detail, but you asked about it. So yes, it is an element in the homotopy of the 3 sphere. It's an element in pi 2p. Pi 2p of S3.
The second 3 apply?
What?
The second 3 is.
Yes, it is. Thank you. Right. Okay. Now, all right. Now, okay. This is the story for. This is the statement for large primes. Primes greater than or equal to 5. Now, there's also a theorem. The status of things for the prime 3 is much less conclusive. So the following is known. Theta 1 exists. Theta 2 does not exist. And that's because of this total differential. But now here's the surprising thing. Theta 3 does exist. There is a class on the atoms. There is a class that fits this description. And we don't know what happens for larger J. Now, I'm going to, toward the end of the talk, I'm going to discuss a program that might lead to a theorem that says that theta j, at the prime 3, theta j does not exist for j at least 5, and that would leave theta 4 open. Theta 3, remember, I erase those numbers. What happened to my numbers?
They're up on the right.
Right, okay, so yeah, 100 and 106 then. Yeah, so theta 4 is in 322, theta 5 is in dimension 970. The dimension roughly triples each time you increase the index by 1. Okay, so how do we do this? Now, I've defined these elements theta j, in terms of how they show up in the classical atoms spectral sequence. Now, they also have names in the Adams-Novikov spectral sequence. That I will talk about now. Now, they live in X2, the appropriate pi degree of X2 of, they live in this group. And from now on, I'm going to drop all these decorations and just refer to this as text, whatever. So, what are they? There are these elements on the Novikov 2 line, the Adams-Novikov 2 line, that have the name beta with various subscripts. And this is the beta that I want. Beta p to the j minus 1 slash p to the j minus 1. Now I say could be, and I'll explain what I mean by that. It's exactly that in the case j equals 1 and 2. But for higher j, there are other elements in the same Novikov bi degree. I will explain. So the formula is so we're in a particular. So what is the bi degree? I should write that down. It's 2p to the j times p minus 1, right? That is the dimension of theta j. Yes. Okay, so the entire Novikov 2 line, the entire X2 group is known. It was computed in the late 70s for odd primes by Miller, Wilson, and myself, and a couple of years later for the prime 2 by Shimomura in Japan, Katsumi Shimomura in Japan. Anyway, this is a known group, and it's known to be an elementary abelian P group of a certain rank, and that rank is roughly j over 2, roughly. Now, I think I can write, let me think. The precise formula is take the floor of, I'm saying this wrong, aren't I? Take the floor of j plus 1 over 2.
Does it survive into x over k, the rather k theory x?
I don't know exactly what you mean by that.
Well, if you mark from BP to k2 and look at the x over k2 side of k2, does it survive?
I'm not sure. I don't know. But anyway, I want to give an example of this. So for the prime 2, so if j is 3, this number will be 2. So so beta 4, 4 and beta 3 both live in the same X group, namely X2, 16, and here for the prime 3, we've got beta 9, 9 and beta 7 both living in this group. Now, why do I mention this? Well, there's a map from the Novikov spectral sequence to the atom spectral sequence, which generally raises filtration. Now, these two elements, so both of these, all of the elements I've written down have Adams Novikov filtration too, but their counterparts in the atom spectral sequence will in general have filtration larger. In particular, beta 3 goes to dimension 4, and I think beta 7 goes to dimension 7, if I remember right. These are two-dimensional. These have filtration too. So when you pass from the Novikov to this atom spectral sequence, these elements get spread out in filtration. And furthermore, a certain linear combination of these two elements is actually a permanent cycle. Surprising. And now notice this beta 7 has higher filtration. So whatever this linear combination is, it's going to show up as theta 3 in the atom spectral sequence, and that's why theta 3 is a permanent cycle. Beta 9,9 isn't, but theta 3 is. Now, how do we actually produce these things? So now I'm going to give you a geometric, sort of what homotopy theorists like to think of as geometric construction. And it involves things known as Smith-Toda complexes. So these were studied in the early 70s. So one of them is V0. That is, this is the mod P Moore spectrum. And Adams showed that Adams showed the following. If the prime is on, there is a map. There's a map like that from this suspension, and it induces an isomorphism in K theory. And so I want to look at the cofiber of that. And that's, I'm going to call that V1. Now, let me remind you what the BP homology of these things looks like. The BP homology of V0 is BP star mod P, and the BP homology of V of 1 is this. In case you've forgotten, the homotopy of the BP spectrum is a polynomial algebra over two local integers on elements V1, V2, and so on, and the dimension of Vn is twice p to the n minus 1. So those are the v's that I'm talking about here. And then there's another statement like this due to Smith and Toda independently. And it says, if the prime is at least 5, there's another map of interest. I'll call beta. It goes like this, and it's multiplication by V2. Now, so we can do the following. So here's a way to construct a lot of elements in the homotopy groups of spheres. Let's iterate this map some number of times. So T is some positive integer. Then this complex has a bottom cell that is in this dimension. And so this is the inclusion of the bottom cell. And it also has a top cell. It's a complex with 4, because of the way it's constructed, it's a CW complex with 4 cells, and the top cell is in dimension 2p, so we get a map like that. And so this composite is a map from a sphere, one sphere to another sphere, and it's known to be non-trivial for all t. So this composite is called beta sub t, and it's known to be non-trivial in all cases. Now, this is still under the assumption that the prime is at least 5. This breaks down, and this does not work at the prime 3. You don't have a map like this at the prime 3, you just don't. Similarly, you don't have a map like this at the prime 2. In both cases, you can get a map by that involves a larger suspension, but that's another story. Now, in particular, theta 1 is beta 1. So this is how you can construct theta 1. It's a case of this construction where t equals 1. That's the element that I'm calling theta 1. Now, let me repeat the Toda's theorem. Toda's theorem is that theta 2 supports a differential. And incidentally, this alpha 1, another way to get alpha 1 is the following. I can take this map here, map in the bottom cell, which has dimension 2p minus 2, take the Adams map, and then I want to pinch out to the top cell here. This only has 2 cells, one are in dimension 0 and 1, so the top cell is in dimension 1, and this composite is alpha 1. And that's the same map that appeared, it shows up as an attaching map in a suspended complex projective space. All right, now it's time to bring in some heavy chromatic machinery. Okay, so the heavy chromatic machinery is this. Let's say, let's let IN stand for the following ideal. Now remember, BP star, the homotopy of BP is that polynomial ring on the V's. And now I'm looking at an ideal in that ring generated by these n elements. Then, here's a theorem. Due to Miller and myself, inspired by Morava. And it says the following. Let's say we take, it's an algebraic theorem. So let's kill this ideal in BP star and then invert Vn. Remember my shorthand. If I write X, that's shorthand for all of this. So now I'm doing this for a different variable here other than BP star. I'm replacing BP star by this. And the theorem is, I'm not going to try to state it precisely, but it says this is closely related to where Sn here stands for the N-Morava stabilizer group. Now, I don't want to take the time to define that precisely. I'm hoping you've all heard of it. And it's a p-adic group, it's a pro-p group that plays an important role in chromatic homotopy theory, and this is essentially that role. It's also known to act on the Lubin-Tate spectrum, and its homotopy fixed point spectrum is blah blah blah. This group is a major player in chromatic homotopy theory. Let's leave it at that. And you can read about it in lots of papers. Okay, so now here are some facts about this group that are relevant to us. Okay. If n happens to be this number, p minus 1 times p to the I, then Sn has a subgroup that is isomorphic to the cyclic group of order p to the I plus 1. So that means there is a map from the cohomology of Sn, however it's defined, to the cohomology of this subgroup. So I want to consider okay, so for p equals, or if p is at least 5, let's consider the following. Let's take X for BP star, which is the Adams-Novikov E2 term that's converging to the p-local homotopy of the sphere spectrum. Okay, now we can map BP star into this gadget. And then we can map that we have a theorem that essentially equates this with, if you understand it properly, it equates it with the cohomology of this stabilizer group. And okay, so then depending on what n is, I can map this to the cohomology of some finite group that happens to be sitting inside Sn. Sn itself is an infinite group, and its finite groups have been classified. There are not very many of them. There's only a finite number of finite groups. In some cases, that number is 1. In some cases, the only finite subgroup is the trivial group. But anyway, as I've noted, in certain cases, the group has a subgroup that's isomorphic to that. And so in those cases, you can get a homomorphism from the Adams-Novikov E2 term to the cohomology of a finite, say a finite cyclic group. Now you know exactly what the cohomology of a finite cyclic group is, so you can ask yourself, what are the images of elements of interest here, over here, and what can we learn about them? So, I can't reach this. Can't reach all of this blackboard right now. Okay, so if the prime is at least 5 and n is p minus 1, that means we have a subgroup of order p in there. And and let's say we're mapping to the mod p homology of the cyclic group with p elements. We know what that is. I'm going to write it like this. It's an exterior algebra on a one-dimensional class, tensor to polynomial algebra on a two-dimensional class. Now, I'm using the symbols alpha and beta, but I don't mean to imply they have anything to do with this alpha and this beta. But anyway, alpha lives in H1, beta lives in H2. Now, here's the cool thing. The element that I've called alpha 1 maps to the element that I'm calling beta. Now, I've left something else. I've left something out here, and that is either you have to introduce either you have to tensor this with kn star, or you have to collapse the grading. And I don't want to get tangled up in details like that. But anyway, here's here's a much stronger result. Theta upper I means some monomial in the thetas, any monomial in the thetas. Not any polynomial, but any monomial in the thetas has a non-trivial image here, and it's the appropriate power of beta. Theta itself, each theta j maps to this class beta, and any monomial in the thetas maps to the appropriate power. I guess that follows from the first statement. Now, the monomials in beta do not have linearly independent images here, but every monomial has a non-trivial image. Now, what is this bias? There's another piece of information that I have to give you before I can give you the proof of the theorem of the prime for large primes. And it's this. In X over the scheme of algebra, there are certain relations among betas such as here's one such relation. Theta j to the p times theta j plus 2 equals theta j plus 1 to the p plus 1. You can check that that both sides of the equation have the same dimension. And there are more relations like that. Anyway, I'm not going to walk you through all the details of this, but the point is, with the help of these relations, it's possible to deduce right, okay, so I'll do one of these. Okay, so theta 1, theta 3, theta 1 to the p, theta 3 is theta 2 to the p plus 1. Now, let's calculate the first differential in the Novikov spectral sequence. It goes like this. Now, we know that theta 1 is a permanent cycle. And on this side, we can use the Leibniz rule, and we can get a formula like this. Now, d of theta 2 was the subject of Toda's theorem. So, okay, so we know what this is. We know it's that. Now, what does this buy you? If you could divide through, notice that both sides have a theta 1 to the p in them. Let's say I could divide by that. If I could divide by theta 1 to the p, I could conclude that the differential on theta 3 is alpha 1 theta 2 to the p, and that's modulo the kernel of theta 1 to the p. Now, because of, what happened to my monomials? Where did my monomials go? Oh, yes. Okay, the fact that all the monomials have non-trivial images means that we don't have to worry about elements that are killed by theta 1 to the p. This element is not killed by theta 1 to the p. So that means that modulo this indeterminacy, this is non-trivial. And we can make similar calculations on all of the thetas this way, using other relations of this sort. And these relations up here are sort of internal to the Steenrod algebra. This doesn't involve any chromatic homotopy theory, it just involves the Steenrod algebra. All right, now, so the differential I'm talking about is the 2p minus first differential in the spectral sequence. So all those guys support differentials. And so you can use Toda gives us the first one, and then these relations and this detection thing that's now hiding up there is what enables us to leverage all of this. Now, this is all for primes at least 5. It's all for primes at least 5. Now I have to tell you what goes wrong at the prime 3 or at the prime 2. Now, let's see. Okay, let's go back to this statement here that says, for selected values of n, the Morava stabilizer group has a cyclic subgroup of order a power of p. Let's go back to that. Okay, so I'm going to write this down again. If n is 2 minus 1 times p to the I, then Sn contains a subgroup isomorphic to this. Now, you have to do this for, and if you want to play this game, the game that I just played here, you have to have n bigger than 2. N has to be strictly larger than 2 in order to detect all theta j's. If n is not bigger than 2, then you're gonna run into problems detecting these things. So in particular, if I was looking at, so for p equals 3, the second Morava stabilizer group contains an element of a group of order 3, but this is n equals 2, so that's not going to do it for us. The next opportunity is this. The sixth Morava stabilizer group has a group of order 9 in it. So if we could somehow get into that group, we might be in business. Now what happens for p equals 2? Well, for p equals 2, S1 contains a group of order 2. S1 just happens to be the 2-adic units, and that group has an element of order 2 known to us as -1. That's the element of order 2. S2 contains a group of order 4, but a cyclic group of order 4, but again, this is too small. The next opportunity is S4, which has a group of order 8 in it. So these are the two cases that potentially can detect theta j's, and this one does detect theta j. Now,
Sorry, why do we need n at least 3?
n bigger than 2, because if n is 2, then you're going to be detecting all the elements. You're going to be detecting lots of elements on the 2 line, including those guys. You won't be able to distinguish at the prime 3. Remember, there was a problem with beta 9, 9, beta 9/9, and beta 7, and a linear combination of the two of them is a permanent cycle. And I forget exactly what happens, but you're not going to be able to tell those two things apart if n is 2. You need n bigger than 2 in order to flush out the unwanted elements in the 2 line. You want to flush out. You want the undesirable elements on the 2 line to go to 0, and you want the theta j's themselves to map in non-trivially. And in order to get that to happen, you need n bigger than 2. All right. Now, so let me remind you now. So let's think about this case for a minute. One of the mainsprings of this proof for large primes, the 40-year-old proof from the 70s for large primes, was Toda's theorem that said there was this differential in the spectral sequence that says theta 2 isn't a permanent cycle because blah, blah, blah. Now, at the prime 2, there is no such theorem. For the prime 2, there's no such theorem. And if you try to generalize Toda's argument to the prime 2, you'll find that you're calculating a derivative, a differential on something, and the answer you get is something that was 0 to begin with. So you're not going to get an interesting result. There's no analog of Toda's theorem. And the substitute for Toda's theorem, instead of using Toda's theorem as the linchpin, we use the gap theorem instead. And that's the theorem that says pi minus 2 of the magical spectrum omega is 0, and then by its periodicity, that's the same as 254 of omega, and that is where theta 7 is supposed to live. If theta 7 exists, you're going to see it here, but the group is 0, so theta 7 doesn't exist. So at the prime 2, we need a gap theorem in order to get the non-existence of the higher thetas. And at large primes, you can use Toda's theorem. There may be a gap theorem too, but nobody knows how to prove it. Now, the reason nobody knows how to prove it, you're going to say, well, why can't we just use the same technology that we use at the prime 2? The answer is we don't know how to start. There is no analog of MUR. I'll explain what I mean by that.
This is an example of a much needed gap.
What?
This is an example of a much needed gap.
This is an example of a gap we'd like to fill. An example, this is not a... There was this joke about some professor saying, your paper fills a badly needed gap in the literature. I will lose no time in reading it. You're supposed to ponder the double meaning of that statement. But this is not a badly needed gap. This is a gap we'd like to get rid of. All right, so here's the big problem. Well, let me remind you how we got our magical spectrum omega. We started out with MUR, which is a C2 spectrum. And then we did something to it. We normed it up to C8. We did some equivariant construction to it to get to this magical spectrum omega. Now, if we wanted to do this, and the important thing is that this is a C2 spectrum. This spectrum came equipped with an action of C2 with suitable properties. And so if we wanted to do this, do a similar thing at a larger prime, we'd need to start with a CP spectrum of some sort. The problem is nobody knows what that is. Now, I'll tell you what it might look like. So let's just call this mysterious spectrum X. X might have the underlying homotopy type of the twofold, or let's say the p-1 fold wedge of MUs, maybe. And so these are things that we want. Maybe. Maybe we're looking for a spectrum that's underlain by the p-1 fold smash product of MU, and somehow CP is acting on it in an interesting way. And the action should lead to the following: the geometric fixed points should be an HFP module. HFP means mod P Eilenberg-McLean spectrum. Now, in the case of the prime 2, the geometric fixed points of MUR is MO. That's the unoriented cobordism spectrum, which was shown by Tome in the 50s to be a wedge of mod 2 Eilenberg-McLean spectrum. That fact is crucial to our proof. So in order to make an odd primary analog of the HHR calculation, you need some spectrum that looks roughly like this as a substitute for MUR. It's supposed to have a CP is supposed to be acting on it in a suitable way, and the action is required to be such that the geometric fixed points is some sort of HFP module. Nobody knows how to construct such a thing. This is the problem. Nobody knows how to do this. So I will stop there. Thank you.
One thing I wanted to ask you was, the original TODA differentials, are they related to power operations?
Yes, they are. Yes, they are.
So that's true for the thetas as well?
Yes, they're related to power operations. It's sort of it's an extended power construction. And as Maholtz said many times, if you do the same thing at the prime 2, you'll get something that's already dead. You'll find, it'll say, you'll get a statement that says there's a differential on theta j plus 1, whose target is eta times theta j squared. Woohoo! The trouble with that is that eta times theta j squared is 0 in the atom spectral sequence already. So that differential doesn't do anything for you.
And the other question I was going to ask, I think you've still got it on the, oh, maybe there was another board, maybe you've rubbed it off. So what you're doing is you're starting with X over BP. You're mapping into the localized X, which is basically the X over Kn.
Something like that,
and then
yeah.
you project off into the
Then
stabilizer.
you use the connection with the Morava stabilizer.
Yeah, but I mean but then you push across to the cohomology of the stabilizer group.
Yeah.
But I mean, in some sense, are you pushing the differentials into another spectral sequence whose E2 terms are those group cohomologies? So
No, you're not, there isn't necessarily a spectral sequence on the other side. We don't know that there's a, so I said we're going to take Vn inverse BP star mod In. Now, that isn't necessarily the BP homology of a spectrum. In fact, it's very likely not to be. That's like asking for a TODA complex for, say, a TODA complexes that don't exist or are not known to exist.
So it's not something like a Lubin-Tate spectrum smash with a
Smash with what? That's the problem. You want to smash it with a TODA complex, but there's no TODA complex to smash it with. That's the problem. So anyway, this thing is not the homology, the BP homology of a spectrum. And it doesn't have to be for the proof. It's merely a method of detecting, showing that certain things in the original spectral sequence are non-trivial. It's a detecting it's an algebraic detecting apparatus. And it isn't, you're not mapping to another spectral sequence. You're just mapping to another X group.
Yeah, I see what, yeah, okay.
Anyway, the big problem, as I said, is nobody knows how to construct this CP analog for an odd prime. That's the big mystery now. If we could do that at the prime 3, my guess is that we would get a periodicity of dimension 972, which is 2 more than the dimension of theta 5. We get a gap theorem as before. We get that pi minus, maybe I should write this down. properties that this omega might have are satisfies a detection theorem, satisfies a periodicity, and I'm guessing on 972, which is 2 more in the dimension of theta 5, and it has a gap theorem. Pi minus 2 equals 0. If all of that happens, what you will get out of that is that you'll get a non-existence of theta j for j at least 5. Now remember, we already know theta 1 and theta 3 exist. Theta 2 does not exist. That's already known. This would leave theta 4 open, just like at the prime 2, where theta 6 is still open. Anyway, the big theorem would be that theta j does not exist for j greater than or equal to 5. That's if everything happens the way I hope it does. But we're a long way from being able to do that because, as I said, we don't know how to construct a CP analog of MUR, so we don't know how to start.
And how important is it that it has, if it existed, it would have that so much powerful?
Well, you can do calculations, making various assumptions. I've tried this. It might even be, the periodicity might even be 486 instead of 972. It really wouldn't matter. You'd get the same conclusion. The important thing is how many powers of 3 divide the periodicity. And I'm betting that it's got to be 3 to the 5th times something.
Thank you again.
My pleasure.